Good afternoon, everyone, and welcome to my presentation. My name is Pedro Paulo Medeiros Ribeiro. I am from the Federal University of Rio de Janeiro, the Polytechnic School, and the Department of Metallurgy and Material Engineering. In my presentation, I will focus on the hybrid route to extract nickel and cobalt from laterite ores. The title of this presentation is Nickel and Cobalt Extraction from Laterite Ores. This job has been developed by me, by Professor Achilles, and by Professor Iranils Daniel dos Santos. Nickel presents a wide range of applications in industry, especially in the production of steel, which accounts for two-thirds of its consumption. The world nickel primary production consists of 42% from laterite and 58% from sulfide. However, when we talk about the deposits, laterite ores represent 3/4 of all the nickel sources, while sulfides represent 1/4. These images show the sulfide ores and the laterite ores, the aspect of each kind of mineral. Nickel and cobalt prices. Cobalt and nickel prices have reached high levels. Cobalt upsurged in price after 2019, trending to move positively and reached more than $70,000 per ton in 2022. Nickel upsurged in price in 2016, trending to move positively and reached more than $22.5 thousand per ton. Laterite ores are divided into three main types, which until now have largely been treated differently to release the nickel within. The limonite ore, which contains from 0.8 to 1.5 of nickel and 40 to 50% of iron, is processed mainly through the hydrometallurgical routes, such as acid leaching. The transition ore, which contains from 1.5 to 4% of nickel and 25 to 40% of iron, is processed mainly through the pyrometallurgical routes or a hybrid route called Caron process. The saprolite ores, which contains from 1.8 to 3% of nickel and 10 to 25% of iron and 15 to 35% of magnesium, is processed mainly through the smelting routes. The sulfation roasting leaching basically consists of sulfating the ore sample with concentrated sulfuric acid at room temperature plus water. The sulfated sample is subjected to heat treatments at temperatures ranging from 200 to 700 degrees in one or more states. In this case, it was done in two states. The first one, called pre-roasting, done at 267 degrees Celsius for 60 minutes, and the second heat treatment, called roasting, was done in the temperature range from 680 degrees to 830 degrees for 20 minutes. So after the sample's heat treatment, the sample is cooled to room temperature and finally leached with water. During leaching, water-soluble sulfate dissociates, leaving metallic ions in solution. Iron, after heat treatment, tends to remain as oxide, which presents low solubility in low acid water solution. So, iron concentration in the pregnant leach solutions is low. And finally, the filtration of the The leached product will give us a PLS, which is the pregnant leach solution, and the solid leaching residue. The pregnant leach solutions will be carried to make the chemical analysis and finally the mass balance, while the solid leaching residue will be analyzed by SEM EDS scanning electron microscope and EDS plus XRD. Finally, the samples were quantified by the Rietveld method. So, how the road works? First, the sulfation. The main mineral present in the ore are goethite and hematite. They will react easily with the sulfuric acid to form ferric sulfate. Due to their instability in the temperature range used, the trivalent sulfates like the ferric sulfate and aluminum sulfate will decompose, releasing SO3 during the pre-roasting and during the roasting steps. This sulfur trioxide will react with other metals oxides present in the ore sample. The temperature range evaluated tends to increase the formation of metallic sulfates, such as those of nickel and cobalt, which are more stable than iron and aluminum sulfates. For different samples of nickel laterite ores from different regions of Brazil were investigated. The samples were denominated limonite W, red limonite X, limonite rich in chalcedony Y, and limonite Z. It was received 5 kilograms of each sample. All the samples were quartered using a Jones rifle sampler. The dry sieve was the technique used to make the sieve of the samples. It was performed by a Rotep sieve shaker. The chemical analyses were done by atomic absorption, and the roasting tests were carried out in a muffled furnace. The X-ray diffraction analyses were performed with Bruker D4 Endeavor diffractometer with cobalt radiation, iron filter, and the position sensitive detector PSD. For the quantification of the minerals and the phase present in the ore, it was used the Rietveld method-based mineral quantification with a fundamental parameter approach, in which the software used was the Topaz 5.0. The crystal structure information for the minerals was supplied by the Bruker structure database. The image analyses were performed with a scanning electron microscope coupled to an energy dispersive X-ray spectroscopy system and the detector. The composition of the raw ore after drying for sample W can be observed in this slide. The iron content was higher than 30%, while nickel, cobalt, and magnesium contents were higher than 2, 0.1, and 4%, respectively. It's also possible to see the quantification of the main nickel and cobalt carriers in this ore. The sample W was composed basically by quartz, goethite, chromite, lizardite, hematite, chlorite, and magnetite. The main nickel bearing phase are chlorite with more than 73.6%, goethite with more than 19.4%, and lizardite with more than 5.4%. For samples X, Y, and Z, nickel, cobalt, iron, magnesium, and silicon content, as well as nickel distribution in the main minerals, can be observed in the following table. Other minerals can be asbolon, tridymite, or amorphous phases. The characterization of the ore samples was carried out with dislimed samples. However, for processing tests, samples were processed without disliming. The content of the minerals present in the sample during Each step of the processing can be observed in this figure. The main sulfate phases found after the pre-roasting and roasting heat treatment were morusite, which is nickel and cobalt carrier, magnesium sulfate, chromium sulfate, quantitite, and roastite. It can be observed that the percentage of the last two phases decreased considerably after the roasting step, while the amount of magnesium sulfate and morusite increased. In terms of mass, however, magnesium sulfate showed an increase of about 6.5 times as compared with the amount found at the pre-roasting step. Morusite, however, had a 9.3 drop in mass verified after the roasting step. There was a substantial increase in the amount of hematite, around 400%, in the residue when compared to the quantified in the raw ore sample. This results mainly due to the transformation of goethite to iron sulfate and their subsequent composition to hematite and the decomposition of non-reacted goethite. Furthermore, in the case of silicates, the acid attacks the structure of the thiosilicates, breaking the bonds of the octahedral and tetrahedral layers, leading to the dissolution of the elements of the phase and transformation of also leachable amorphous silica. This attack explains the decrease in the amount of chloride, indicating that this mineral reacted with sulfuric acid and/or the gas SO3 or decomposed during the thermal processing. Apparently, the quartz content increased in the solid lithium residue. However, after calculating the mass of this phase, it was observed that the amount did not vary significantly at any step of the process, except for the pre-roasting step. In this step, a height value for the quartz mass was found. Probably, this value was overestimated from the quantification. The quality of the refinement was analyzed by the mathematical parameters RWP and goodness of fit, which indicate the quality of the refinement, and they were in the range from 2.35, 2.80, and 1.69 and 1.88 respectively. These values are indicative of good quality refinement. The visual inspection of the obtained and calculated diffractogram spectrum, as well as the residual difference of the measured and calculated diffractograms, also present a very good fit. The relationship among the four main phase component found in the samples X, Y, and Z and in the processing residues is present in this figure. It can be noted that quartz and hematite content in the residues increased substantially in relation to their concentration in the original ores. This increase is essentially due to the conversion reactions of ferric sulfate formed during sulfation and pre-roasting, as well as the reaction of minerals containing silicon in their structure to form quartz. The amount of laterite in X and Y samples was quite different, 34 and 10% respectively. But in their lithium residues, both were smaller than 1.6%. These results make evident that practically all of the magnesium present in the laterite octahedral sites reacted with the acid during sulfation or with the gas released during the roasting step. The decrease from 34 to 1.5% of serpentines, mainly laterite, in the X sample also indicates that almost all of the nickel was extracted from this phase, and goethite is the phase in the residue with more nickel. The higher amount of magnesium solution from serpentines affected the extraction of nickel incorporated into goethite. The amount of goethite in the X sample, unlike the Z sample, can be considered high and equal to 5%. The scheme exhibited in this figure exemplifies the mineral phase change involving nickel, cobalt, and iron compounds for the sulfation roasting step before leaching. The main idea is to obtain nickel and valuable metals such as cobalt in the form of sulfate, while iron should remain in the form of oxide to reduce the acid consumption. The best results were obtained by the sulfation at room temperature, followed by pre-roasting at 265 degrees for 60 minutes, roasting at 780 degrees Celsius for 20 minutes, followed by cooling until room temperature and leaching with water. The nickel and cobalt extraction were higher than 80% for samples W, X, and Y, while for sample Z, the iron content was high, but the most significant analysis was the nickel extraction, which was smaller than 77%. This is explained by the amount of amorphous phase found in the sample and also because of the high amount of magnesium. Conclusions. The mineralogy of the solid lithium residues of laterite ore samples determined by X-ray diffraction includes hematite, quartz, goethite, chromite, ilmenite, lizardite, vermiculite, tridymite, and spinel. Amorphous phase was also detected in some samples. The success of the road depends on the decomposition of iron, aluminum, and magnesium sulfate during the roasting. However, magnesium sulfate does not decompose in the temperature range of the process, increasing the acid consumption. The application of the sulfation roasting lithium process for nickel and cobalt extraction from laterite ore is promising. More than 80% of nickel and cobalt were extracted under favorable conditions. The authors wish to thank the Instituto Tecnológico Vale, the Brazilian Research Agency, NPQ, and Professor Dilson Silva dos Santos.